In this video, I will show how to solve this second-order differential equation subject to the condition x equals 1, y equals 1, and dy dx equals 3 at x equals 1. We will use the method of undetermined coefficients. If you do not know how the method works, you can take a moment to study it and then come back to the video. To begin, we will introduce the substitution t equals ln of x to simplify the right-hand side, so that we have x equals e to the t. We want to get rid of all the x's and have a differential equation involving only y's and t's. To do this, we want to find d squared y over dx squared in terms of dy dt and d squared y dt squared, so we first need to find dy dx in order to proceed. To find dy dx, we will differentiate y x with respect to y. dx dy is given by d dy of e to the t, which is just e to the t dt dy by the chain rule. When we invert this, we have dy dx equals e to the minus t dy dt. To find d squared y dx squared, we will now differentiate the dy dx which we just found with respect to x. So, d dx dy dx is given by d dx e to the negative t dy dt. To evaluate the derivative, we will use the product rule. We first differentiate e to the negative t with respect to x, so we get negative e to the negative t and dt dx as a result of the chain rule. Then, to differentiate dy dt, we get d squared y dt squared by normal differentiation and dt dt as a result of the chain rule. But then we have a problem because we don't know dt dx. To find dy dx, recall that t is just ln of x. So, dt dx is d dx of ln of x is just 1 over x. Remember, we don't want any x's, only y's and t's, so we can substitute x to get 1 over e to the t, which is just e to the negative t. We can now substitute the expression for dt dx into the expression we've previously found for d squared y dx squared. So we have negative e to the negative t times e to the negative t dy dt plus e to the negative t of d squared y of dt squared e to the negative t. And we have two e to the negative t terms, so they multiply to become e to the negative 2t. And this is the d squared y dx squared term. Now we are ready to rewrite the original differential equation in terms of the new variables t and y. The e to the 2t term nicely cancels out the e to the negative 2t terms, leaving us with a differential equation that is much easier to solve. As I mentioned previously, we will use the method of undetermined coefficients to solve this differential equation. For the left-hand side, the auxiliary equation is given by lambda squared minus lambda minus 6 equals 0, so that we have lambda minus 3 times lambda plus 2 equals 0, so lambda is 3 and lambda is minus 2. Recall, when the discriminant is positive, i.e. when we have two real roots as in this case, the complementary function is given by y equals ae to the alpha x plus be to the beta x, where a and b are arbitrary constants and alpha and beta are the roots of the auxiliary equation. Therefore, in our case, our complementary function is given by y equals ae to the negative 2t plus be to the 3t. For the right-hand side, we will try the particular integral y equals pt squared plus qt plus r. Differentiating once, we get dy dt equals 2pt plus q, and differentiating again, we get d squared y dt squared equals 2p. We will substitute these expressions into the left-hand side. We can then equate this to 2 minus 2t minus 6t squared to find the coefficients of p, q, and r by matching the coefficients of t. We find that p equals 1, q equals 0, and r equals 0. So our particular integral is given by y equals t squared. The general solution is given by the sum of the complementary function and the particular integral. So y equals ae to the negative 2t plus be to the 3t plus t squared. Now we can substitute back the original variable x and get rid of all the t's. Our general solution is therefore given by y equals ax to the negative 2 plus bx cubed plus ln of x squared. To find the particular solution, we will find the values of the arbitrary constants a and b by substituting x equals 1 and y equals 1 into the general solution. From this, we get the 1 is equal to a plus b. Then, differentiating the general solution and substituting the value of 3 for dy dx, we get that 3 is equal to negative 2a plus 3b. When we solve this simultaneous equation, we get a is 0 and b is 1. Therefore, the particular solution to this second-order differential equation is given by y equals x cubed plus ln of x squared. Thank you for watching, and if this video helped you, please make sure to like and subscribe. We'll see you next time.